All right, we'll go ahead and get going, everyone, so we could get through. We have a lot of information to get through today. My name's Eric Balejos. I am the Public Information Technology Officer for Northwest Mosquito and Vector Control District. I'm also the committee chair for the NBCAC Training and Certification Committee. I'd like to introduce Mike Niemela this morning. He's a senior public health biologist for California Department of Public Health, and he's going to be going over each session this morning and this afternoon. We're going to have time for some questions, hopefully, at the end of each category. If you have any questions, if you could please put those in the chat, and then I could get those to Mike at the end of his presentation in between each category. Other than that, I think we're all ready, Mike. It's over to you.
All right, sounds good. Thanks. To make sure this. All right. Well, good morning, everybody, and welcome to the Category A review session. This is for the pesticide application and safety training for applicators of public health pesticides. So I just want to say that viewing of this webinar does not it's not a considered replacement for studying the Category A material in its entirety. How do I get these windows? There we go. Okay, great. This program will help you focus your study efforts, but will not necessarily cover all aspects of the exam. So I've summarized the more important sections of the exam, but you can find the additional information with the link below. Okay, so first of all, we're going to talk about agencies, state and federal laws. We're going to talk about definitions, label information, talk about pesticide formulations, PPE, first aid, conversions, and sample questions. So let's talk about agencies, state and federal laws. So the California Department of Pesticide Regulation, or CDPR, or just DPR, that oversees pesticide usage in California. The California Department of Public Health oversees the vector control training. That's why I'm talking to you, and the certification program in California. So DPR relegated that responsibility of regulating the public health use of pesticides to CDPH. Notice I say public health. And then the County Ag Commissioner's Office, they oversee pesticide usage in the counties. Why is this not advancing? Okay, there we go. Okay, so let's go over FIFRA. So FIFRA is the Federal Insecticide, Fungicide, and Rodenticide Act that was signed into law in 1947 and established the requirement for registration of pesticides by the U.S. Department of Agriculture. The U.S. EPA registers the pesticides based on FIFRA and EPA guidelines. The U.S. Department of Agriculture enforces pesticide tolerance levels on food and raw agricultural commodities. So if you're out spraying and you happen to spray an organic field, you could be running afoul of the U.S. Department of Agriculture guidelines. Okay, let's talk about the NPDES permit. NPDES stands for National Pollution Discharge Eliminating System. It's a permit authorized by the Clean Water Act of 1972 that's designed to reduce pollution in streams, lakes, and rivers and wetlands and other waterways from point source discharges. In 2011, this became applicable to pesticide applications, including vector control, to or near waters of the U.S., and we'll go over waters of the U.S. in a moment. For pesticide treatments to water of the U.S., the California State Water Resources Control Board has a permit that is mandatory, and its stipulations must be closely adhered to. The permit requirements are subject to change, and technicians should check with their supervisors for the most current regulations. Okay, so this is a very busy slide, and I'm not going to read everything in its entirety, but the waters of the U.S. is basically all waters which are currently used or were used in the past or may be susceptible to use interstate and foreign commerce. So basically, waters of the U.S. includes wetlands, interstate lakes, rivers, streams, etc. Also includes a territorial sea and wetlands adjacent to waters identified in the earlier paragraphs. Essentially, what you have is basically all streams and drainage ditches draining into a stream, catch basins that drain into delineated wetland, and rivers. Okay, those are all considered waters of the US. So essentially, you're going to assume that all waters that you're dealing with are waters of the US, except for a few caveats. So dairy ponds or catch basins that drain into a sewage treatment plant are not examples of water of the US. And you should be aware that irrigated agricultural fields usually are not considered water of the US until that runoff leaves the field. So they are not waters of the US within, say, a rice paddy, but when they take the dam out or the check out and all the water runs off, then that water is considered waters of the US. And that definition is subject to change, so it's best you talk to your supervisor and your district for their policies. Okay, let's go into definitions. Okay, the following definitions are interconnected. I don't want you just to memorize what the definition is. I want you to understand, kind of like on a three-dimensional level, how all these definitions are interconnected. For example, if you see the term contamination on the exam, you'll need to recognize that contamination might be a consequence of drift. Contamination can be all considered as such because the level detected pesticide violates the stated tolerance of that product. Think organic crops, but also understand that drift is beneficial in some situations and not others. So I want you to understand all these things and not just the individual terms in a vacuum, if you know what I mean. So the first one I want you to know is integrated vector management. You will need to know this for the exam. IVM is the preferred modern approach to vector control, with pesticides use being the last option. Chemicals are only used after all the other steps are proved ineffective. And contrary to popular opinion that a lot of the public has, responsible agencies aren't applying pesticides, willy-nilly and just the first option. And this is based on the modern approach on IPM. Okay, so here is your IVM IPM pyramid. So you have prevention at the base, followed by cultural sanitation, physical, mechanical, biological, and chemical or pesticide at the very top. And we're going to go over each step. Understand that chemicals are the last option, used only after the other steps have proved ineffective, and each ascending step generally becomes more complex and costly. And also understand that each step has its advantages and its disadvantages. So let's talk about prevention. The old expression, an ounce of prevention is worth a pound of cure. So when I say prevention, I want you to think about education, which is also public outreach. So that can come in many forms, including radio ads, billboards, door-to-door campaigns. For instance, when I was a technician at Sac Yellow, one of my jobs was to go door-to-door and talk to the public. There's county fairs, movie theater commercials, mosquito repellent handouts, school programs, etc. So basically, if you can get the public to prevent mosquito reproduction on their property, you'll have less mosquitoes to treat. They're doing their job for you. We want to teach the public the 5 Ds of prevention. And this is, of course, we're in West Nile in mind. So drain, dust on, dress, DEET. All these are very handy in protecting the public from mosquito-borne diseases. So here's some of the educational pamphlets that we have. So we have Fight the Bite. This is in English. We have it in Spanish. We have it in what appears to be maybe Russian or Thai, I'm not sure. So we have it in a bunch of different diseases, languages, excuse me. And also remember that you are the face of the district. So part of the reason why we're educating you as technicians is, one, so you won't hurt yourself with pesticides, but also so when you go out to talk to the public, they come away with the interaction of you thinking that you know what you're talking about and they have every confidence in your abilities. So you are the face of the district, so it's helpful to know what you're talking about. It's also helpful to have patience when you're dealing with the public, because oftentimes there'll be misinformation you're dealing with or just outright hostility because you spray pesticides, and a lot of communities are adamantly against that. It's helpful if you speak other languages. When I was a technician, speaking Spanish was definitely an asset. Some of the advantages: an educated public will be involved. Educated public will be involved public. So a lot of times children are your best bet, because once you can convert the children to your way of thinking, they'll often drag their adults, their parents, into their projects, which include dumping out flower basins or wheelbarrows or what have you. And it's generally good PR. So the people you're dealing with are taxpayers. They pay for your salary. And if they're left with a good impression that their money is well spent, then you've done your job. Now, the disadvantages to getting out and talking to the public is that it is time consuming and it can be labor intensive. The advantages of this will always outweigh the disadvantages. So, for instance, in 2011, the Aedes albopictus infestation in Southern California was detected because the public notified the district about day-biting mosquitoes. And concerned communities won't necessarily change their minds regarding pesticides, but maybe you can calm their fears enough to do your job. The next level of the pyramid is cultural sanitation. And this is the elimination of pest sources through policies or practices. So if done properly, this can be a win-win for proposition farmers, the public, and mosquito control districts. For example, you can take manure and spread it on the field rather than having it be in big piles, which produce a lot of flies. So another example is switching from flood irrigation to drip lines. So this is a win-win because there won't be flood irrigation, water standing around producing a lot of mosquitoes. It also saves water, much more efficient to drop the water at the base of the trees, exactly where it's needed, rather than flooding the whole orchard. Again, there are the advantages. This can save the farmers money, which will also, people follow their pocketbooks, so this will allow for community buy-in, and it may save time. So now, instead of dealing with a flooded orchard, you're dealing with perhaps maybe a few pools where maybe the drip line was broken and it made a pool at the base of the tree rather than the entire orchard. You can contact UC Extension or abatement districts for expertise. And some of the disadvantages are maintenance may be time consuming. It takes maybe more time to actually patrol the orchard looking for broken drip lines rather than one giant pool you're dealing with. And it may require constant repetition or vigilance. The next level is physical mechanical, and that's basically making physical changes to an area by mechanical means to prevent pests. And that could be you with a shovel or multi-million-dollar projects. But you have to weigh, and this one's a little tricky because you have to weigh cost versus the benefits, because sometimes it can be financial. How much money are you going to sink into a project? It could be ecological. Are there sensitive species in the area, sensitive habitat, and administrative? Do you have to get permits to do what you're doing, or can you just go out and do it on your own? So an example of physical mechanical is cleaning the weeds and debris out of drainage ditches. So if you have all that grass and emergent vegetation there, it's going to be very difficult to treat the mosquitoes that are being produced. But if you get rid of the grass, obviously it's a lot easier to reach the water and the mosquitoes. It could also be draining swampy areas to prevent mosquito breeding. It could be altering a river channel. So now instead of a floodplain where you may have pools of water accumulating, you have just a center channel, probably the LA River, and mosquitoes don't like flowing water. So if you can keep the water flowing, then all the better. There's also removal of beaver dams, which often involves population control, but this part may be tricky. You may have to get permits, but the public health needs may trump the needs of the beaver. The advantage are you're physically changing the area, which can prevent or reduce the number of pests without the use of chemicals, and it could be a long-term solution. And as such, it can save money. Disadvantages, again, you may be dealing with sensitive habitats, presence of protected species, and constant maintenance to may be required to keep it pest-free. As part of physical mechanical, herbicides can also be used to clear paths to mosquito sources. Understand that with the gold card from CDPH, it does not authorize you to spray roadside ditches and that sort of thing unless it has something to do with mosquito control. Usually it's to get rid of emergent vegetation in the water or clear paths to a source. So our gold card that you'll be earning is not carte blanche to spray herbicides. The next level is biological or biocontrol, and that's making use of natural enemies such as predators or parasites or pathogens to reduce the pest number. And the most famous example is the mosquito fish, Gambusia. Their native range is through northern Mexico, through southern Indiana, and tributaries of the Mississippi River. My former employer, Saciolo, produces between 2,500 and 5,000 pounds of Gambusia annually. And they'll introduce these into various ponds or lakes or even rice paddies to control mosquitoes. They also use guppies, which are native to South America, and they can use these in highly polluted environments like sewage pools, dairy lagoons, etc. And their areas are useful in areas with low dissolved oxygen that aren't acceptable to Gambusia. And they're affected by the cold. So if you release them in an area, then they'll die out in wintertime and it won't persist from year to year. So perhaps you don't, because of some sensitive species, you don't want them there all year. The advantage of the biocontrol is that natural enemies will reduce the numbers of pests without the use of chemical pesticides, and some populations are self-sustaining. The disadvantages, they're not always an option because of sensitive habitats, and they can be slow acting. You may have to introduce them repeatedly, and then sometimes they have been known to disrupt the native environment. Now, keep in mind that BTI and BS are bacteria, and some people consider those to be biocontrol, but we're going to, just for argument's sake, we're going to include those in chemical control methods. Okay, the very last point of the pyramid there is chemical pesticide, and the use of chemical pesticides to control a pest in the last option of the IVM pyramid. For example, fogging a residential neighborhood with a chemical pesticide. Advantages of this are immediate reduction in pest numbers versus biocontrol, and it's useful to prevent or manage disease outbreaks. So if you have dengue transmission in your neighborhood or West Nile or something along those lines, and you really need to knock down the number of mosquitoes, the most immediate way to do it is chemical pesticides. Disadvantages of the chemical pesticides can promote resistance among pest populations and could anger the public. You can also have non-target issues. You have contamination, which is drift, persistence in the environment, and other important considerations. It also can be expensive to apply flames, operate trucks, pay for the product, etc. An example of chemical control is fogging your neighborhood. And again, you have immediate reduction in pest numbers. It's useful to prevent and manage disease outbreaks. And the disadvantages, again, are the use of chemical pesticides can promote resistance. You could have non-target issues, and I want you to think bees in this case. You have drift, persistence, and expensive to fly planes. Now, I repeated that because you may see that at some point in the exam. Okay, in vector control, we have a limited number of tools in the old toolbox. So long story short, IVM was designed for environmental protection and the prevention of pesticide resistance. We have a finite number of products that have been labeled for mosquito control. Many of the pesticides are either related chemically or by mode of action or both. So within a family, if you start getting resistance to one product, you might have resistance to other products. And our collective nightmare is our products won't work because of resistance. So that's why we have implemented the pyramid that we've mentioned, IVM pyramid, because mosquitoes won't get resistant to you dumping out a saucer and killing them. Okay, susceptibility. That's the degree which an organism can be injured or affected by a pesticide at a known dosage or exposure. An organism that is affected by a pesticide is called a susceptible organism, and the opposite of resistant. And what is pesticide resistance? Pesticide resistance is the ability of the pest to avoid the post-exposure lethal effects of pesticides. I stress lethal because pesticides can often knock an insect down, but it will recover. Now, the resistance can happen through spontaneous mutations in populations resulting in genes that confer pesticide resistance, or because a small proportion of the population carries a gene for pesticide resistance naturally. Okay, let's talk about selective pressure. And before we talk about resistance further, you'll need to understand two concepts: phenotype and selective pressure. A phenotype is a set of observable traits in an organism. In humans, that would be hair color, height, eye color, etc. Genetic variation causes people to have different phenotypes. If you look at a crowd of people, we all look different for one reason or another. A selective pressure is a force that causes a particular phenotype to be more advantageous or less for survival in certain environmental conditions. And that could be anything: pesticides, heat, cold, predators, disease, food type, etc. So in other words, if you were to take a woolly mammoth, if they were still around, and take one and drop it into the summertime in Arizona, all that hair would be a disadvantage. But if you were to take that same woolly mammoth and place it in the Arctic, then it would be an advantage. So in other words, phenotypes will interact with selective pressures, making it more likely or less likely that an animal will survive to pass its genes on to the next generation. And ultimately, that's what we're talking about: surviving to pass its genes on to the next generation. So here's a perfect example here. So you have a generation of mosquitoes, you have 10 mosquitoes. The one with a random mutation is going to be resistant to the pesticide. The other 9 are not. And that random mutation could be anything. So maybe that particular type of mosquito, they're all the same species, but maybe that individual has a thicker cuticle and therefore less susceptible to pesticides. The other 9 have a thinner cuticle, excuse me. So you spray them and you're left with just a few survivors. But one of those survivors is the one with the random mutation. The other 2 survived for one reason or another. Maybe it was just luck. Maybe they were inside something. They weren't exposed to the pesticide. So all those mosquitoes mate. Now all of a sudden, they're far more. Now 40% of that group is resistant to the pesticide. You spray them again, and you're left with a few survivors. There's only one now that's susceptible. The rest are survivors or are resistant. Then you have your next generation, which are 90% resistant. You spray those, and the cycle continues. So it's a perfect example of why we try to use the IVM pyramid rather than just spraying, and why we also rotate products within our arsenal of controlling mosquitoes. So to determine resistance, we evaluate the efficacy of products through what's called bottle bioassay, excuse me, where basically mosquitoes are in a lab or exposed to known concentrations of a pesticide, and we see at what level they are killed. There's also efficacy trials in the field where you'll have say a ULV application, and then you'll have within these little cages there, you'll have mosquitoes at known distances from the spray. And then you track to see at what point the pesticide affects the mosquitoes or does not affect the mosquitoes. Okay, so residue is the amount of pesticide that remains in or on a plant or animal or on a surface after a pesticide treatment. So that can result from a direct application, from drift from nearby fields, from uptake from contaminated soil, or from other sources. Now, residue is not always bad. It's desirable in some situations to produce prolonged effective pest control. In other words, residues can be a source of unwanted and illegal contamination on food or feed or crops, or they can be beneficial. Depends on the situation. And you have to be aware of organic crops because typically speaking, you don't want any sort of pesticide on those. Now, when you're dealing with residue, you have to ask about persistence. How long does that pesticide remain in the environment? Factors include rate of application, soil temperature, exposure to sunlight, microbial and chemical decomposition, solubility of the herbicide, and precipitation. When you deal with residues, there's also tolerance, which is the legal limit of the amount of pesticide that can remain in or on food. These limits are established by the US EPA and are enforced and monitored by the FDA. Pesticide residues are usually measured and expressed in parts per million, parts per billion on a weight basis. For example, 1 part per million is 1 milligram in a kilogram, or 1 ounce of salt in 62,500 pounds of sugar, or 1 pound of pesticide in 1 million pounds of raw agricultural commodity. When pesticide tolerances are found to exceed legal tolerances, the agricultural commodities involved may be seized and destroyed. Ordinarily, such situation would arise from the application of agricultural pesticides on crops. However, pesticide deposition could happen when applications are not specifically targeted at a crop pest, such as the application of pesticides on rice fields for mosquito control. Okay, potentiation, that's when you have an increase in toxicity, usually an undesirable one, of a pesticide when combined with 1 or more pesticides. So you have, if you add pesticide A with pesticide B, often because of potentiation, the resulting product will be much more toxic than either A or B. A synergist is a material that's not necessarily pesticides themselves, but make a pesticide ingredient more effective at killing pests. For example, piperonal butoxide, PBO, is usually mixed with pyrethrins and acts as a synergist. Without using a PBO, a technician should have to use much higher concentrations of pyrethrin mix, which is obviously something we're trying to avoid, to achieve the same results achieved when using the PBO pesticide combination. But PBO itself may have a long residual life in aquatic systems. Okay, contamination, same thing as pollution, which is the deposition of a pesticide in an unintended area. The undesirable persistence of a pesticide after unintentional or intentional application, and may lead to an adverse incident report submitted to the CDPR and CDPH. So one of my jobs, besides being a biologist and doing the CE program, is I have to report adverse incidents to CDPR. So I get those several times a year. Sometimes it's the fault of the technician. Sometimes it's bad luck, like a traffic accident where there's pesticide spilled in the street. But nevertheless, all these things have to be reported to CDPR. And if there's contamination on organic crops, there'll be some trouble there, and you don't want to be involved in that. Okay, so target organism, that's the definition of a pest at which the pesticide application or other control method is directed. That's to differentiate from non-target organisms, which such as bees or others. That could, a non-target could be anything from dragonflies to some other birds or some other insect that you're not intending to control. To avoid targeting non-target organisms accidentally, you must use your knowledge of the target organism's biology to decide when to spray. Okay, LD50, TD50, and ED50, lethal dose, toxic dose, and effective dose. Basically, the dosage of an active ingredient that kills 50% of test animals, or signs of toxicity in 50% of test animals, or the dose at which predefined effects occur, which is effective dose. Okay, terms related to dose effect relationship. So no observable effect level is null. Is the highest dose that results in no observable change in 50% of the test population. Toxic dose, again, is the dose that will produce signs of toxicity in a certain percentage of species of animals. And lethal concentration, LC50, usually used for toxicity testing for exposures to pesticides in the vapor state, such as fumigants. All right, pesticide drift. Those are airborne. Pesticide drift, by the way, can be your friend and your enemy. So it's basically airborne particles produced during application of a pesticide moving outside the intended treatment area. The longer the effective drift of the product, the greater efficacy. Except with aerial and ground-based ULV applications, drift is an undesirable side effect associated with pesticide applications. Pesticide labels specify that ULV applications must be done during weather conditions that favor pesticide drift, which are temperature inversion or lateral winds below 10 miles an hour. Okay, there's a bunch of factors that affect pesticide drift. One is the formulation of the product. Obviously, dusts are more likely to drift than granules. Spray pressure, high pressure sprayers are more likely to produce fine droplets that are more susceptible to drift. Bad maintenance, so if you have improper or worn nozzles or excessive pressures. And the size of the droplet. Small droplets can drift further than larger ones. And there's also evaporation, which really is more the case of herbicide formulations, which may or may not be relevant to vector control. You should avoid drift because it wastes resources, including pesticides, fuel, and technician time. It spreads pesticides into the surrounding environment where they may become illegal residues on food crops, cause health problems, damage wildlife, and have other undesirable effects. It could damage sensitive crops, and it's been the cause of many a damage claim for crop losses. Okay, you should understand how temperature inversions work. Basically, that occurs when the temperatures at the ground level are lower than temperatures at higher altitudes. That's the exact opposite what you normally see, because normally the sun heats the soil, so the air right above the soil is usually warmer than it is at higher altitudes. So during an inversion, cold air is trapped by the warm air above it, and there's little vertical mixing. And the small droplets produced by ULV sprays remain suspended in the cool air within several feet of the ground, which is advantageous if you're trying to kill female mosquitoes. And this is because at the time of spraying, female mosquitoes are host seeking, looking for a blood meal near the ground level, and the risk of the damage of non-target organisms is low. Without lateral air movement or temperature inversion, without the temperature inversion, basically the vertical air currents will carry the small droplets well above the level the mosquitoes are operating, flying around. And so basically you'll be wasting money. Heat rises, and with the inversion, the trap droplet, without the inversion, the trap droplets, your pesticide would rise well above the ground. Okay, you should be familiar with pesticide labels, and this is one for Anvil 1010. You should understand about the signal word, which is danger, warning, or caution. And these are assigned based on the most severe toxicity category, assigned to the 5 acute toxicity studies. And if methanol is present in a formulation in a concentration of 4% or more, it's automatically considered danger. The signal word is required to appear on the front panel of all pesticide labels, along with the statement, keep out of reach of children. I want you to remember that, keep out of reach of children. Okay, so here are the toxicity category for pesticides, and I want you to understand danger, warning, and caution. This is in the category A PowerPoint for the manual, so you can go through this at your leisure, but we're not going to spend a whole lot of time on this slide other than danger, warning, or caution. Okay, you should be familiar with SDSs and labels. The safety data sheet, if you have an older form, it may be called an MSDS, but safety data sheet is the current terminology. And this is the information about hazardous ingredients and properties of the formulated product, the health effects, toxicity, or toxicology, excuse me, accident, transport, and handling procedures. The label will go over the active ingredient, use directions, and precautions. The label, you should understand, is a legal document. You can't, if the label says you have to apply in such a way, that's the way it has to be applied. You can't freelance and do your own thing. When should you read a pesticide label and the SDS? Before you buy the pesticide, before you transport, mix, or load it, before you apply, before you store, and before you dispose of unwanted pesticides in the empty container. All right, let's talk about pesticide formulation definitions. Emulsifiable concentrate are concentrated oil solutions of technical grade pesticides mixed with an emulsifier added to permit further mixing with water. So emulsifiers are basically detergent-like materials allow for suspension of very small oil droplets in water to form an emulsion. They're widely used in vector control operations, with the final water dilutions being made in spray tanks, and the mixes tend to be milky in appearance. They're losing their popularity somewhat with the rise of the cost of petroleum products. There's also wettable powders, where finely ground dry powders consisting of active ingredients are mixed with other ingredients to aid mixing and dispersion. They're intended for mixture with a liquid, usually water, for application by spray equipment. Generally mixed with water to form a slurry before being added to the spray tank, and they require constant agitation. Wettable powders are harder on equipment than other formulations and cause wear on pumps, gaskets, and spray nozzles. There's also soluble powder, which is similar to wettable powders, except the added ingredients, as well as diluent, and all the formulating ingredients are completely soluble in water, and uses are similar to those of wettable powders. There's also dust, finely ground mixtures of active ingredients in the carrier material intended for direct application without further mixing. You never use dust where you think drift is going to be a problem. So CDPH, we use dust to treat campgrounds. So we use those if there's a plague outbreak or there's fleas or a problem. So we apply those directly to rodent burrows and bait stations to control fleas and plague operations. Fumigants typically not used very much in vector control, as far as I know. They're more used in structural pest control, but they're volatile chemicals that are stored as liquids under pressure, incorporated into solid form with clay, and release toxic gases combined with water vapor. And it's used for vector control of rodents and their associated ectoparasites on the ground. Granules are probably your best friend, especially when you're treating vegetated areas. Basically, the active ingredient is mixed into various clays to form particles of various size. These require specialized dispersal equipment that may be applied from the air or the ground, may be used a small hand cranked or scattered by hand. Of course, you'll be wearing personal protection when you do that. Useful in treating mosquito larvae where heavy vegetation to prevent insecticide from reaching the water where drift could be a problem. There's also baits. Baits contain active ingredients that are mixed with the food or attractant. Principal uses are these for household pests such as ants, mice, rats, roaches, and flies. Used outdoors to control birds, ants, and slugs. Snails and ag pests such as crickets and grasshoppers. There's also aerosols, which are pressurized cans, contain a small amount of pesticide driven through a small nozzle under pressure from an inert gas, which is called a propellant. Often used to control household pests like flies and weeds and structural pest control. Their use peaked in the 1990s and since then have dropped significantly. There's also a water-soluble concentrate, which is a liquid formulation that can form true solutions in water and require no agitation once mixed. They are used the same way as the emulsifiable concentrate. There's a flowable. Flowables are usually are a liquid usually mixed with water for use in a sprayer. Forms suspension in water, which requires continual agitation. Principal uses are similar to those of emulsifiable concentrates. Okay, ULV, so ultra low volume. This is a chemical applied under a very fine spray at low application rates, typically droplet sizes between 10 and 30 microns. Okay, slow release formulations can be encased or encapsulated in inert material for controlled release, releasing and decrease hazard and likelihood of the active ingredient reaching the target, or excuse me, the increased likelihood of the active ingredient reaching the target organism. So sustained release mosquito larvicides are based on this principle. Methylprene briquettes slowly release a juvenile hormone analog to disrupt metamorphosis. So often these slow release formulations are used in like catch basins to control mosquito larvae. So you don't have to come back and treat them every week. Okay. Water pollutants, it's extremely important to know that that those planning to apply pesticide directly to bodies of water will be completely familiar with and follow federal label directions pertaining to any material being used in or around water, including posting notice of the application when required by the product label. Okay, let's go over PPE, protective equipment. Okay, so the hazards associated with the contamination by any pesticide vary with the type of pesticide and the route of exposure. By wearing protective clothing and using available safety devices such as face masks, goggles, and gloves, the danger from contamination by pesticides can be minimized. Okay, the information about the required safety devices and clothing is available on the pesticide labels and on the safety data sheets. Personal and environmental safety devices should be available at all work sites where pesticides are handled, mixed, or used. And the use of pesticide safety clothing and other safety devices should never be a substitute for taking common sense approaches or precautions when using pesticides. Okay, skin contamination is the leading cause of occupational pesticide-related illness. Therefore, protecting the skin should be given first priority. So coveralls, aprons, spray suits, gloves, hats, boots, et cetera, are designed to protect the pesticide users from getting the pesticide in the skin or into the eyes. Okay, I want you to study protective clothing, such as lightweight disposable coveralls, washable coveralls, aprons, et cetera. So I want you to go in to chapter 7 and review the category A PowerPoint and review that very closely. You'll need to know about protective clothing. For example, natural rubber gloves provide protection from organophosphates. Unlined flexible plastic gloves are the best for all other pesticides, provided they were designed for use with solvents and pesticides. Make sure you read the label for PPE requirements. Okay, here is a list of the glove category selection key by DPR. And this is also in the category A PowerPoint. I want you to actually review this, including the gloves must be at least 14 mils or greater, except for those made of laminate and polyethylene materials. So I want you to understand how this chart works. Okay, first aid. Thoroughly review the first aid section of chapter 5. I'll say it again. Thoroughly review the first aid section. Know the first aid steps for poisons in the eyes, inhaled poisons, swallowed poisons, and chemical burns of the skin. Know how to post emergency information, name, number, address, doctor, etc. Know where this information should be posted. Okay, if you are around somebody who gets poisoned, so first of all, stop the exposure immediately. Give CPR or artificial respiration if the vehicle is not breathing. If the highly toxic material is on the victim's mouth or respiratory path, use chest compression, not mouth to mouth. Decontaminate the victim by washing off any skin residues, or residues of pesticide on the skin, and remove any contaminated clothing. Speed is absolutely essential in this step. The label and SDS should be consulted for specific first aid instructions, so don't just guess, actually read the label. If you're exposed to a pesticide while working alone, remain calm. Just understand that symptoms of pesticide poisoning from vector control products usually are mild and take time to develop. If you're alone, if you're alone with the victim, you must first give attention to the victim, especially if it's starting breathing and separating the victim from the pesticide source and decontaminating the victim's skin. If another person is with you and the victim, one should perform first aid and the other should seek professional help. Due consideration must be given to the protection of yourself and other personnel in the vicinity of the incident, especially if it's a large pesticide spill. Remember what I said about trucks often, or not often, but in the past, I've seen trucks where trucks have had someone collide with the truck and spill pesticide. Okay, the following should be clearly posted in a prominent place, such as near the telephone in the main post office or district office, excuse me. So Poison Control Center, National Pesticide Information Hotline, Chemical Transportation Safety Center number, and the regional poison control centers of California. Understand that they're in Sacramento, Madera, San Diego, and San Francisco. I also want you to understand conversions. So I want you to understand 1 acre equals 43,560 square feet. 1 mile equals 5,280 feet. I want you to understand the interchangeability of gallon, fluid ounces, pints, and quarts. 1 pint, 16 fluid ounces. 1 pound, 16 ounces. And at 1 mile per hour, you travel 88 feet in 1 minute. So I want you to understand these. Okay, I'm going to give you a few sample questions here. Okay, you're calibrating your sprayer. You find that your sprayer is putting out 8 fluid ounces per minute of spray, and it takes 16 minutes for you to spray an acre of land. How much spray per acre is your sprayer putting out? I'll give you a second to work on that. That's 128 fluid ounces. So basically you have 8 fluid ounces per minute times 16 minutes per acre. So you have 128 fluid ounces. And how many gallons? Okay, so sample question 2, if you wish to spray a pesticide at a rate of 4 pints per acre, you have 5 acres of land to treat. How many pints of pesticide should be placed in the tank? The answer to that is 20 pints or 320 fluid ounces. Okay, a vehicle traveling at a rate of 12 miles per hour will travel how many feet in 30 seconds? And be sure you know how to do this. As a technician, you'll be doing similar calculations. Basically, it's 528 feet. So remember, if you travel 88 feet per minute at 1 mile per hour, so that would be 1,506 feet if you were to do 12 times 88. Divide by 1,056 by 2, since you're calculating distance traveled over 30 seconds rather than 60 seconds, equals 528 feet. Okay, that's all I have for you for category A.